Okay, so this next video is all about work done. So when we're talking about work done, okay, often work done, we forget that it actually is talking about some sort of energy transfer that is taking place. And I think because we don't use the word energy, we use the word work, students often forget that actually work, therefore, is measured in joules. Now, in this case of calculating work done, we have an equation, but remember, because it is an energy transfer, we can often equate this to our other energy equations. So, for example, I could equate it to kinetic energy. If it's work done in stretching a spring, I could equate it to potential energy of a spring, elastic potential energy. If it's lifting something up, I could equate it to mgh. So just be really careful, because it is an energy transfer. That work done, we have a main equation, but we can also link it to our other energy equations. So when we define the work done, okay, it's the force multiplied by the displacement. And again, we have to look at it in terms of the force acting in terms of the displacement that's going on. So we actually have to look, if I've got an example of box here, and I'm pulling my force at a slight angle, I can't take this size of the force. I have to use the force in the direction the object is moving. Okay, so I'm going to use my trigonometry to break it up, and I'm going to have to take here the F cosine theta component of this force, because it's the part of the force acting in the direction that the object is moving in. So my force, again measured in newtons, S being displacement, so it's in meters, and our cosine theta, just be really careful. Your calculator needs to be in degrees. Again, often in our exams we're switching between the two, so just double check your calculator is in degrees there. And again, that theta is the angle between the force and the direction of the motion, because we want the force to be in the direction of the motion. And again, work done is measured in joules. So looking at this, because we have this cosine theta, there is a certain situation when no work is done. Now, if no work is done, this becomes equal to 0, which is essentially when we are at cos 90. So rather than saying at cos 90, I would say no work is done is when the force is at 90 degrees to the displacement. Okay, so no work is done is when force is perpendicular to displacement. Now, a really common one for this, for example, is in circular motion. Okay, imagine, again, we've got something moving around in a circle. Well, the force is our center-seeking force, so it's acting down. But our displacement, our direction that our velocity is acting, is always going to be at 90 degrees. So often we link it back to circular motion when no work is done. So just remember, we've got the equation here that we can calculate. You might need to consider it being at an angle. We might have to also relate this to other equations, so kinetic energy, potential energy equations as well. And I'm going to just do a little example here at the bottom. So this is one that we did use in class. It's just a nice little one. It would be a very simple one marker in there in the exam. So having 100 Newton force is applied at an angle of 30 degrees to the horizontal to move a 15 kilogram box for 5 meters. How much work is being done? Well, in this case, my box is moving horizontally along, okay, a distance of 5 meters. I've got this 15 kilogram box here, and it's at an angle of 30 degrees. So I write out my equation. Again, please get into the habit of writing out your equations in exams. W equals Fs cos theta. Well, my force in this case is the 10 newtons, so 100 newtons. So I'm going to put my 100 in. My displacement was 5 meters, and the angle was at 30 degrees. So this was given to 433 joules, which is about 430 joules if I'm giving it to two significant figures here. I didn't need to know the mass of the box, okay? The force is the force that's pulling it, okay? In this case, I'm not looking at the mass of the box there, all right? So I didn't need to use that one in. You might have to use masses though, for example, if we're using things vertically and we're having to work out the size of the force or the resultant force pulling it up against the weight. So you might have to consider those masses at some point. The other thing that often gets asked with work done is often to do with graphs. And we can look at force displacement graphs. Remember, again, with elastic potential energy, this could be like the force versus the extension. But but I'm just going to leave it as force displacement. So again, using the equation, W is equal to Fs cos theta. Well, in this case, I'm just going to be using Fs because Fw is equal to F times S. The multiplication of this, okay, is essentially the area under the graph. So the area under the graph is equal to the work done. Really common for multiple choice questions. It might get you to calculate how much work has been done in a certain displacement. It could just be simply identifying that work is done, but you might have to do a simple calculation. So again, if it's triangle, just remember your area is equal to a half your base times your height. They have made this a little bit tricky there in the past, and it sometimes really freaks students out when instead of giving them F against S, they give them A against S. Now remember, this F here is our resultant force acting on it. So in this case, I'm going to be using my F is equal to MA. Okay, now because this is A over here, we actually can write our equation out as W is equal to MAS. Well, because this is A times S over here, that's equal to W over M. So the area of the graph in this case is the work divided by the mass. So if I wanted to find out how much work was being done for this, I'd have to do the area under the graph multiplied by the mass of the object in this case. Okay, so that's just another little one there that has come up on the multiple choice questions before. It is a little bit more advanced, but it is still using the same principles as the one from above.